Now I want to introduce partial derivatives. So let's start with our usual setup, f maps E to Rm, where E is an open subset of Rn. And this first part is just going to be building up a bunch of notation. So there are some projection maps. Let's call them pi up through pi m, projecting the various the m components of Rm to R. So like the ith projection map, the first projection map would send these things to the first coordinate, and so on. So then we can define fi to be pi I composed with f. So this would be from the domain of f to Rm, and then from Rm project to R. So like that. And these would be called the components of f. Component functions of f. So it's not that f itself is an m tuple. It's not. F is a function. But by composing f with projections, you can have these things that would also be called components of f. And the way they operate is that if you... Sorry, shouldn't do that. If you write out f of x as a vector, it's the first component of f at x. I mean, as an m tuple, then it's the first component of x, comma, the second component of x, of f of x, up to the mth component of f at x, like that. Okay, so that's just notation so far. So now, if you're going to talk about the derivative of f, if it exists, the derivative of f at a point would end up being this kind of map, right? So a linear map from Rn to Rm is something that you can represent by a matrix. And in order to get a representation, you need a basis for the domain vector space and a basis for the codomain vector space. If you focus specifically on the standard basis in each case, then when you write down your matrix representation, you find that you get the partial derivatives, which we have not defined. So we will also define partial derivatives. But let's just get the notation down for the bases. So we'll use E1 through En for the standard basis for Rn. Standard basis, you know what that means. E1 is the vector 1, 0, 0, 0, etc. And then we'll use U1, I'm basically just following Rudin's notation, through Um as our standard basis for Rn. Then assume, well, no need to assume actually. So it may or may not exist. This directional derivative may or may not exist, but you could, anytime you want to, take the, I think this is the notation the textbook uses, take the directional derivative of f along the direction E sub j at a point x, where here x is some point in the domain E. So such a derivative might or might not exist, but when it does exist, we're going to call that sorry, let me do this to the ith component of f. When this does exist, we're going to call that a partial derivative, and we're going to define, so what I'm writing down now is defined to be this directional derivative. So this is going to be defined like this, just d sub j f sub I of x. And remember, when we defined directional derivatives earlier, this was defined to be the derivative with respect to t at t equals 0 of fi of x plus t ej, like that. So in the previous lecture, we defined directional derivatives like this. We didn't do it just for. We didn't insist that the direction vector be a standard basis vector. We allowed it to be any vector. But now I'm saying when you make it be a standard basis vector, then you get something that we also have another notation for, and we call it a partial derivative. So this is called a partial derivative. And of course, it's, if you write out the limit definition of this thing, it is the partial derivative that you're probably familiar with from many other contexts, where you treat a bunch of the variables that are inputs to f as constants, and then you let only one vary at a time, and you take a derivative with respect to just that one. So it's the familiar partial derivative. Let's see. So let me tell you which definition this is, I guess. It is 916. So this is definition 916. Is this.